So yes, hello everyone. My name is Jinsu Park, and I was a graduate student in the Bernardi Group, I think until 2022. And then currently I'm an assistant professor at the Department of Physics at Post-Tech Korea. And today I will talk about the developments in Perturbo about electron-phonon interactions using not just DFT in LDA GGA, but using DFT plus U and DFPT plus U, the Hubbard-corrected density functional theory. Uh, okay, so as you have seen from previous lectures and hands-on sessions, first principles electron-phonon interaction can be now applied to various semiconductors and transitional metal oxides. So these are some of the just many examples that you have already seen. For example, we can study charge transport properties. So this is the electron mobility as a function of temperature for famous semiconductor gallium arsenide that has been done in 2016. And we can also study real-time electron non-equilibrium electron dynamics. So we can put electrons in a non-equilibrium population and see how they move as a function of time back into equilibrium. And we can study more complex materials, for example, such as strontium titanate, which has polarons. And we can calculate the spectral function of this material, even if it has polarons, and see some phonon sidebands. This is all calculated in Perturbo. And on top of that, we can also study charge transport properties as a function of temperature even in the presence of these polaron, which give very accurate the temperature dependence and the theoretical calculated predicted results compared to the experiments. But now the question is, can we use this interesting framework for other materials that uh, exhibits interesting phenomena? So, for example, there's a class of material that are strongly correlated electron systems. But unfortunately, we cannot use the previous framework as is, even though if these classes of materials exhibit interesting properties such as high TC superconductivity, Mott transition, multiferroicity, and giant magnetic resistance, the previous workflow cannot be used as is, and that is because it is very hard to even obtain the ground state of these systems using the widely used practical DFT within LDA and GGA. So I'll touch briefly on the reason why that is. So how do we get the ground states of these correlated electron system? Well, in general, once we are given a material, so this is cobalt oxide that I'm going to use as an example, but any kind of material, if we are given a crystal structure, our goal is to simulate and calculate the solution to the many-body Schrödinger's equation that has many electrons that are interacting with each other via this Coulomb interaction. But of course, we cannot do this exactly, so we need an approximate solution. And in the Consham DFT framework, we treat these electrons as an independent electron that are interacting with a effective mean field potential. And this is the Consham Hamiltonian that many of you are familiar with, I am sure. And a lot of the electron-electron interactions are uh, encoded in this exchange correlation potential. And this exchange correlation potential is theoretically, it can be exact, but it is usually obtained from the LDA and the GGA perspective. So the density functional is only evaluated using a density that is at some position and or some its derivative. So every electron feels the same potential using this LDA or GGA. But there's an issue when we try to apply this LDA and GGA to localized D or F electrons, material that have these D and F electrons. Well, one of the key features of these electrons is that they are very localized. So these are unlike S and P orbitals, they have many nodes in their wave function, so uh, they can be very localized. And when you look at their electron density is also very localized in space. And as a result, these within the framework of LDA or GGA, these orbitals are very prone to the so-called self-interaction error. So when we obtain this exchange correlation potential within this LDA or GGA framework, what happens is that since the density created by these orbitals are extremely sharp, the exchange correlation potential is also very sharp around these electrons. And as a result, it strongly interacts with itself through this very strong exchange correlation potential at that position. And that is unphysical because now it means that these electrons are interacting with themselves. These are most severe for partially filled D and F orbital system that are that are the core of many of these correlated electron systems. A widely used way to mitigate this error is the so-called DFT plus U, or the Hubbard-corrected density functional theory. And I'll just briefly go over the main idea for that. The main idea is to separate the electrons into two subsystems. The first, the localized orbital system for the D and the F electrons. The second, the delocalized S and P electrons. And once we separate them into these two subsystems, we separately treat the electron-electron interaction. So for these localized D or F electrons, we use the orbital-dependent Hubbard interaction, which can be represented as this. So it has this U term, that's the effective Hubbard parameter U, and a summation over all occupied pairs, the combination of the occupation of the pairs of these orbitals within the subspace. And for the electrons that are delocalized, we treat them using orbital independent one electron potential, such as LDA or GGA. So in this DFT plus U, now the new functional gives us energy that looks like this. So the total energy is now total energy from the exchange correlation functional is now the original one from the LDA or GGA. And now we add in a new part that was not within this LDA framework, but within the Hubbard U potential. And then we subtract out the ones from these localized orbitals that are included in this LDA. So this is called the double counting term. So as a result, the total energy from the exchange correlation potential now looks like this. We have the LDA term and the Hubbard U related term that I just described before, and then we subtract out the double counting term. So that's the basic main idea. And if you want to learn more about the formalism behind this DFT plus U, you can look into these very excellent references that I have shown here. And as a result of this DFT plus U, there are significant changes to the wave function. For example, if you just use the plain LDA or GGA, then these D and F wave functions tend to be more delocalized and itinerant throughout the crystal. That is one of the reasons is because the system tries to stabilize itself to lower the energy by fractionally occupying many of these states. But now if you use DFT plus U, now the orbitals are more localized and centered around the atoms, and the occupation factor now becomes an integer. So for example, three of these might be occupied and two of these might not be occupied. in contrast to the plain DFT or GGA. Okay, so let's look at one example. So if you use the DFT+U for the ground state calculation of a mud insulator, I'll tell you what happens. So I'll use cobalt oxide, which is a prototypical material that's an antiferromagnetic mud insulator, where DFT fails to describe the ground system. So on the right, we have the density of states as a function of energy. And the zero of energy is the Fermi level. So what happens if you just use plain DFT with an LDA or GGA? Then what we see is that there's a lot of density of states around this Fermi level. So LDA or GGA predicts this material incorrectly to be a metal. But now if you use DFT+U, the Hubbard corrected DFT, now the formalism correctly predicts this material to be a wide bandgap semiconductor of a bandgap of 2.5 electron volts. So this is a mud insulator. In conventional band theory, it's incorrectly predicted to be a metal, but due to strong electron-electron interaction, the material is in fact an insulator. Okay, so that's the gist of DFT+U, but now there can be, so now let us look at the phonons. So for phonons, what we usually calculate is from the framework of DFPT. So what do we do here? We introduce a non-periodic lattice perturbation with a wave vector Q to the system. This Q is not commensurate usually with the system's translational invariant vector, but we can compute the total energy second derivative with respect to the atomic displacements, U kappa Q. So once we do a second derivative with respect to all possible atomic displacements, then we can construct a dynamical matrix and obtain the phonon dispersion, phonon eigenvectors, and so on. And along this way, we compute also the first order response of the electronic density and the perturbation potential caused by these phonons. So this is the first order correction to the density, and this is the first order correction to the constant potential, which the electron feels. This is the phonon perturbation potential. So similarly, we can do a similar thing, similar framework now for DFT+U. So the phonons calculated here follow the same logic. We introduce a non-periodic lattice perturbation with a wave vector Q, but and we also compute the total energy second derivatives with respect to the atomic displacements within DFT+U. So we construct a dynamical matrix and the phonon eigenvalue vectors from this DFT+U framework. And along the way, we compute the first order response of the electronic density within the framework of DFT+U, and also the perturbation potential within the framework of DFT+U. And a new phenomena that happens here, a new quantity that appears, is that this phonon perturbation potential is now divided into two parts. The first, the Consham potential part, and the second, the Hubbard U part. So these both act on the electrons as a perturbation potential. And for the those of you who are interested, you can look at these two excellent references for more details. So what happens? So these are the phonon calculation in a mud insulator cobalt oxide from DFT+U. So let's look at this uh, phonon dispersion here. This is a phonon dispersion of cobalt oxide calculated from DFPT and DFPT+U. If you use DFPT, then what we see are these large soft modes that appear in many points in the Berlin zone. So that means that the DFPT incorrectly predicts this to be an unstable crystal. But now once we use DFPT+U, then all the phonons energies are positive, and we also see LOTO splitting. So the system is an insulator, and also the system is correctly stabilized to the antiferromagnetic mud insulator. So that's one of the success of the DFPT+U framework. Okay, great. But now what we are going to do is to calculate and see the electron-phonon interaction in the framework of this DFT plus U. It turns out at this time, 2020 and 2021, calculation of the electron-phonon interaction and one-year interpolation workflow within this DFT plus C was missing. So let me tell you what we did back then and the results that we have seen. So the key quantity is the electron phonon matrix element G. That's the overlap matrix between two electronic states mediated by a phonon perturbation potential. So similarly to the conventional way of computing this electron phonon, we obtain the wave functions from DFT plus U, and we obtain the phonon perturbation potential and energies from DFPT plus U. And as I have mentioned before, the uh, one difference is that this phonon perturbation potential now has two parts. The first, the Consham part, and this is the change in the charge density due to this phononic perturbation. The second one is the Hubbard U part. So this one comes from the change in the hopping between 3D orbitals. And so these two have a different physical origin in that respect. And for this work, the Hubbard U values are determined from first principles within a linear response approach. So the U value was not taken as an empirical number. It was calculated from first principles. And we were able to make up a workflow, develop a workflow that can calculate these electron phonon interactions at an arbitrary point in the Brillouin zone. So that involved technical challenges such as rotation of these phonon perturbation potential from the irreducible point in the Brillouin zone to the reducible point in the Brillouin zone, and also the interpolation of these electron phonon matrix elements within DFT plus U to an arbitrary point in the Brillouin zone. Well, this is a challenge common for the cobalt oxide that I used as an example, but and also for other classes of materials. And the good thing is now it's public. So if you are interested in using this DFT plus U framework, you are welcome to use it using Perturbo. So let's look at what would happen if you use this DFPT plus U framework for the electron phonon interaction. So we found that the Hubbard U correction has a dramatic effect. That's a one-line summary, but let's look into it. This is a electron phonon matrix element along some high symmetry line in the Brillouin zone, and the blue markers are from DFPT, and the orange markers are from DFPT plus U. So as you can see, these are very different everywhere in the Brillouin zone. I'd like to make 2 points out here, but that is if you use DFPT, the LO phonon modes, their interaction intensity becomes finite at the gamma point. And second, within DFPT, there are spurious soft modes within many points of Brillouin zone, and this electron phonon matrix element diverge. And this is unphysical. If you use DFPT plus U, now we recover the Furlish interaction, and we see a divergence of the electron phonon interaction for the LO phonon modes. And also, we don't see anymore the unphysical divergences from the soft modes. Uh, so okay, but now let's look at a different aspect, that is the Hubbard perturbation potential and its impact in the electron phonon interaction. So in order to do that, I will analyze the electron phonon self-energy coming from the Hubbard potential and compare that with the density of states of the system. So this is the electron band structure of cobalt oxide. So y-axis is the energy, x-axis is some high symmetry line. And on top of this band structure, what I'm doing here is I'm plotting the imaginary parts of the electron phonon fund self-energy coming from the Hubbard U potential. So what we see here is that this Hubbard U potential induced imaginary self-energy is localized within this energy range. And in order to understand that further, on the right, I have plotted the projected density of states, where this red curve is from the 3D partially filled orbitals, and the black curves are from the 3D completely filled orbitals. So we see that this imaginary particle self-energy originating from the Hubbard potential is focused on this very specific energy range that coincides with the energy range where this partially filled 3D orbitals are living at. So that means this Hubbard perturbation potential, dV hub, selectively acts on the partially filled 3D bands. And that's a feature that we cannot find from conventional DFPT. So let's look at the interaction a little bit further, and here I'll give you some microscopic details of the electron-photon interaction from DFPT plus U. Well, the Hubbard U term affects a lot of variables. It affects wave functions, charge density, and the perturbation potential. And the question is, uh, well, how? So another question is how this Hubbard U term affects these quantity. So this is a deformation potential along some high symmetry line. And what you see here are benchmark results from direct DFPT plus U encircled markers and the total electron photon matrix element from the Hubbard U corrected DFT in orange and electron photon matrix elements, but without this Hubbard U potential that are in the green curves. So what you see is that uh, these two values are in magnitude kind of similar to each other. So it means that correcting the wave functions and the charge density from the Hubbard U correction provides the main improvement. And but nonetheless, we should not ignore this Hubbard U induced photon perturbation potential, and that is needed for quantitative accuracy. And so using this is the first application that we have employed this framework upon, and that is to look at the spectral functions of cobalt oxide. So this is a photon dispersion of cobalt oxide overlaid with electron photon strength, and using this plus U framework, we were able to identify strong Frelich modes for these LO phonon modes. So we could expect that the material have polarons because it is an oxide and it has a very strongly interacting LO phonon modes. And in order to do that, we will use the cumulant expansion approach. Well, here, the interacting Green's function is a combination of the non-interacting Green's function multiplied by the exponential of the cumulant, where this cumulant is the function of the Fund self-energy computed within the Hubbard U framework. So this is the resulting spectral function of cobalt oxide within the Hubbard corrected DFT. And what we see is that at 100 Kelvin, there's a distinctive quasi-particle peak with phonon sidebands that's apart by the energy corresponding to the LO phonon modes that indicates large polaron formation. And as you go to higher temperatures, this quasi-particle peak transforms entirely into a polaronic excitation. And these kind of analysis were the ones that cannot be seen from standard DFPT because they fail to capture the Frelich interaction. So this is just first of the many application that can be done using this Hubbard corrected electron phonon plus electron phonon interaction. So what are the outlooks? Well, for correlated electron system, a typically used method to calculate the ground state is DFT plus U, hybrid functionals, or DMFT. And this work was one of the first directions to study electron phonon interaction, which had the Hubbard U corrected electronic wave function and Hubbard U corrected phonon perturbation potential, and many kind of interesting applications or more developments could follow. And recently, David has combined DMFT to with his electron phonon framework, which he will talk about in the later sessions. So yes, all in all, that's many different interesting applications and theoretical developments to follow. So to summarize, we have developed a first principle DFT plus U based approach for electron phonon interaction in materials with partially filled D or F bands, and we found that the Hubbard-Hue term significantly impacts this electron phonon interaction, and that's essential for capturing the correct physics. And our formalism uncovers the polaron effects that has been missing in conventional DFT for these partially filled D bands, and the outlook is that it can be used to study other correlated electron system with partially filled D or F bands. And thank you for your attention. And now David will give a tutorial on the calculation of DFT plus U within this using Perturbo.
Okay, Jinju, it seems like there's one question about the meaning of partially occupied versus fully occupied 3D orbitals.
Oh, yes. Okay. Thank you for the good question. So in cobalt oxide, there are two spin channels, and one of the spin channels are fully occupied and one of the spin channels, the 3D orbitals are fully occupied, and one of the spin channels, it is only partially occupied. So what you have seen for the projected density of states is the difference of the projected density of states for these two spin channels, the fully occupied and the partially occupied ones.
Another question from
Ask the question.
Hello?
you can repeat it.
No?
Can you hear me?
Yes?
Could you eliminate why the Hubble functionals and the DFT cannot capture the correction on the potential on the energy point?
Sorry, I think I couldn't get that.
Why the hybrid functional and dynamical mean field theory methods don't capture the change to the
Oh, I see. I see. So that's yes. So what I meant by that is that it has not been implemented in Perturbo yet. And they can be done, but it is not yet supported in Perturbo.
Yeah, those are both kind of active areas of research, but there has been some work on it. But yeah.
Another question that we have is how the U value is selected for cobalt oxide. The U value is computed from the linear response theory, and it is computed from first principles. And in order to learn that further, I suggest to look at the references by Andrea Flores, Matteo Coccocioni, or Yuri Timrov for the pioneers in calculating this U from first principles.
Great, thank you. Now we are transitioning to the second part of hands-on and lecture 8 and hands-on session 8 by David.
Okay. So I will keep my laptop muted so that we don't have an echo in the room, I think. But yes. But I should share screen, right?
Yeah, he's unmuted. His laptop is.
My like my input audio of my voice is unmuted, but the output audio is muted. Um, um, okay, so in this tutorial, I'm going to cover basically the steps to do a Hubbard corrected electron phone uncoupling calculation in quantum espresso and Perturbo. Now, the main new things here are the quantum espresso calculations, and these are for most of the material systems we considered, they take a little while. For cobalt oxide, I think they're quite expensive, and then even in this case, I made an example on the simpler, less expensive system of strontium vanadate, but the calculations still end up taking something like 30 minutes, and given that that's all we have, I'm just going to walk through the quantum espresso QE to PERT part. But the full tutorial is available online, so you can go through it. And also, I think that the EPR file is available online, so that can be used for the Perturbo part if you just want to do that part. Okay, so so here I'm logged into a cluster, and what I'm going to do is the calculation will start. Let me see if I can zoom in here. Oh, it's too much. Okay. The calculation will start with the SEF like normal. And the only real modification we need to make is we need to do the choose our Hubbard correction in the SEF. So in Quantum Espresso, the more recent versions, you have this Hubbard U block where you will specify the type of orbital projection and then the type of Hubbard correction. For electron phone uncoupling in quantum espresso, they only have a more limited selection implemented. So I think you can only use the atomic orbital projectors and the Dudarev formulation of the Hubbard interaction, which basically means you have a U but no J. And here we have a U of 2 eV. This is a little bit low, probably compared to what it should be, but this improves the stability for the phonon, pH.x calculation. So that's what we have in the tutorial. And you're going to see, so I've already run this. This calculation itself is very fast. And you'll see, there's a number of things around the Hubbard interaction. So it'll tell me, it's doing a Hubbard corrected calculation and so on. And at various points in the calculation, it will calculate this occupation matrix for the local d orbitals on the vanadium, and so on. And then the phonon step is going to basically proceed as usual. But what's different is I'm going to provide it with the temp folder from the SCF calculation with the U, and then Quantum Espresso will figure out that it's supposed to be using a U here. So if I look at the input, for example, it basically looks the same as it normally would. Yeah. And if I look at the output, you'll notice, so this is just the gamma point. This is the fastest one, and this took about 4 minutes. So the other phonons are going to take in the kind of 10 to 20 minute range, which is, and then there's 10 of them or something, 10 Q points. So that's why it's not super slow, but it's a little bit slow for the tutorial. You'll see it's printing out similar information about the Hubbard interactions, and then it goes through, and there's a for each irreducible representation, there's stuff with the Hubbard occupations and potential going on. And one thing that I should mention is that we have to make a slight change to Quantum Espresso, basically just to write out some information that's calculated. And so I can just show you where that is. What is it? Okay, so it's phone on. Oh, it's capital H. PA, and it's listed in the tutorial as well. Yeah, so it's right in here. These lines basically just output this information related to the change in charge density, I think, in the Hubbard part. And we will need that to create the EPR file. And then there's going to be a few. So we've done the phonon calculation for each Q point, and there's just going to be a few other outputs that we'll put in the save. So we have the Dyn XML files like normal, and we have the DVSEF files like normal, but we also have a change files related to the change in occupation and so on. And then the NSCF and Vonnier calculations basically just proceed as normal, but with the Hubbard corrected output. And then in the NSCF, one line, the same line about Hubbard interactions from the SCF, so I won't go through those. But if we go to the QE to PERT, Perturbo will basically figure out from the quantum espresso outputs that this is a Hubbard corrected calculation. So it'll say, DFPT+U calculation. And it will create the EPR file. And then at this point, the EPR file is basically functions the same way it would in any other Perturbo calculation. So actually, we can do some Perturbo calculations. I'm actually going to start these running because they take about 5 minutes. I'll start them running, and then I'll talk about some of the outputs from the quantum espresso. So here this is just a pretty simple script to go into these different directories and run bands, phonons, electron-phonon coupling, setup in sigma and transport calculations. So you've probably seen these calculations before. So I won't go into them that much, but just to illustrate running them with the Hubbard corrected inputs. But yeah, so to kind of revisit some of the stuff from Quantum Espresso, if you were to do the bands calculations and you looked at a range of different U values, you would see something like this. So you'll notice that in contrast to cobalt oxide, where there's the addition of the U creates an antiferromagnetic ordering and creates orbital and spin polarization. The addition of the U doesn't change the band structure very much in strontium vanadate. And the reason for that is because strontium vanadate does not have static magnetic ordering. It's paramagnetic. And it also does not have orbital ordering. So it's perfect cubic. And the T2G orbitals are each going to be equally filled. There's, one electron for the 6 orbitals, or 3 orbitals with 2 spins. And then the EG orbitals, which are these ones, are unfilled. And so there's basically no real change in potential felt in the equilibrium structure for these orbitals. Now, if you want to treat the electronic structure more accurately, you can do this with several different beyond DFT methods. So this would be something like self-consistent GW or dynamical mean field theory. And what you would find is that the key thing is that you would be working with correlated spectra, so like a Green's function based approach rather than non-interacting bands. And because of that, you'd see a normalization in the dispersion. So the dispersion would decrease by almost a factor of 2. The shape would be similar, but the dispersion would decrease, but you would also have a transfer of spectral weight away from the quasi-particle peaks and into like a sort of incoherent part and satellite peaks that are pretty far away. And DFT, kind of no matter what you do, will never do this because you're making a approximation of non-interacting bands and ultimately, taking one band and turning it into a spectral peak here with a satellite here, is just something that can't happen in that framework. So DFT basically, does as good as you can do for the bands in the static in a non-interacting theory. But what we will see is that the Hubbard interaction creates an important change for the phonons, because the phonons involve, breaking the cubic symmetry as they move, and so that will involve different occupations in the different on different sites, and also importantly in different T2G orbitals because there's 3 of them, and the Hubbard interaction will change the response to those phonons, both in terms of the energy and also the potential. So the phonon dispersion and the electron-phonon coupling. So this is the phonon dispersion plotted with U equals 0 and U equals 3, which you could get from doing something like Matt-Dyn after your phonon calculation. And what we see is that there's not a huge difference, but there is, a non-negligible difference, especially for these optical modes, higher in energy, which correspond to distorting the vanadium oxygen octahedra. So these distortions will, in many cases, kind of polarize the different orbitals, and applying a Hubbard U will make it more favorable generally to polarize orbitals. Okay. And just in general, both in this case and also in the cases of the insulators that Jinsu mentioned, it's important to, obviously understand the strengths and limitations of any kind of static DFT-based method, including DFT+U. So DFT+U can correct the self-interaction error in DFT, and so that often can create the desired properties when they originate from things like orbital polarization or site polarization, so changing the occupation on different sites, or spin polarization, so changing the spin on different sites. Things that are kind of intrinsically related to interactions, like scattering rates from electron-electron interactions, or things that are dynamical, such as like anti-ferromagnetic fluctuations or orbital fluctuations without ordering. Those things aren't really going to be captured. But in many cases, it's still, is adequate, and it is a very, pretty like robust ab initio method. Okay, so we can now check on our Perturbo calculations. Let's see, are they still going? They're still going, but they should be almost done. So if I look at the M sigma, okay, so it's 80% done. You have probably seen stuff like this, so I'll just briefly go. For example, the setup, we're using a grid that it's 100 by 100 by 100, but it gets reduced to relatively few K points because we just have a window around the Fermi energy and because we have a lot of symmetry. And then, yeah, the in sigma part will be done in a second. And then, so that's just like normal if you're doing an RTA calculation. RTA is a reasonably good approximation for strontium vanadate because the electron phonon interaction is not that strong. So the Van Migdal approximation is pretty good, meaning you don't need higher order things. And then there is some, backscattering effects that will result in some change when you go to like a full BTE, but it's not super dramatic. Um, so, okay, so now this is done. And then the RTA transport should also, that's not done, but okay, I think I ran it before. So we have this transport coefficients that come out. And these aren't 100% converged because we did it with pretty light parameters, but they should be conceptually correct. And we can see that, conductivity is a function of temperature. And so I'll just go do an overview of what these calculations would look like if you did, you looked at a few different values of U and you did them with higher numerical parameters. So what you can see is that so if you compare the electron phonon coupling at U, so some non-zero value of U versus U equals 0. So this is, in this case, the color map is the ratio of the coupling with and without the U, and the dispersion is shown. So these, you see many states increase the coupling magnitude. And this is particularly the case of some of these optical phonons as well as these transverse acoustic modes. And again, I think this is because DFT+U, by removing a self-interaction error on the local orbitals, it makes the system more favorable to sort of orbital polarize. So, because an electron in a certain orbital of a certain spin is not going to interact with itself. So it's a little bit more favorable to put more electrons in the same orbital. But DFT doesn't really understand that because it has the self-interaction error. It thinks there's a self-interaction happening. By correcting that, you get a bigger response. And then in terms of the resistivity, we'll find that the phonon-limited resistivity is increased by something like 30% for this value of U. And these are some experimental values in different experiments. So this is there's some empirical aspects here, but you can see that probably something related to Hubbard corrections, correlation, self-interaction errors is responsible for explaining a good chunk of the experimental resistivity. Okay, so I think that's all for this tutorial. I'll just mention like so this is on the GitHub, but the full, all the scripts and stuff are linked here. So, yeah, you can try those. They'll take, maybe 30 minutes or something for everything to run. So it's not terrible. It's just a little bit too long. And yeah. I think that's it, but I'm happy to take questions.